So we've done proportional control, we've done derivative control. Now what's left is integral control. And integral control is unique because integral control will immediately place a pole at the origin, right? We can kind of see that right here. Now, the benefits of integral control: improve steady state error, and actually we can drive to 0 for step inputs. We increase the system type, so we have better tracking. So again, we're increasing essentially the order of that system potentially. Actually, we're increasing the order type or system type, excuse me. And we introduce that new pole. So we increase that system to basically third order. Excellent. So when we included KP and KD, we essentially see that denominator will become cubic. And now we're going to actually have to use that Routh-Hurwitz stability criteria or root locus. And we'll see that in just a bit in another lecture. So how can we look at kind of this effective integral gain on stability? So one of the roots is going to start at the origin. As you increase Ki, that pole is going to move left and it stabilizes the system. Other poles, though, can migrate towards the right half plane, so we have to be careful. And if your Ki exceeds a critical value, we can actually create this unstable system. So we have to carefully tune that integral control. So let's say we have PI control. Very, very common control system. So let's look at that PI control. Pole the origin, increase system type now from 0 to 1. We improve essentially that steady state error, increase the order of the system. So second order system, transfer function. Now here we're third order. So we have to look at this and be careful. And we get kind of this kind of messy term in that denominator. We expand it out and we've got this. So this is a third order system. Well, we need to see what conditions of Kp and Ki are we going to actually be stable. So let's go ahead and look at this PI system. PI, not PU, you stink. That's not nice. Anyways, bad jokes today. But anyways, so this is, I've expanded out. This is our denominator. So this is our system. Let's do our Routh table. So 2, 8, Kp plus 200, and then Ki. So this is our Routh table. So now we have some conditions, right? So let's actually take a step. I don't know why it always does this. Actually, here it is. So we now have some conditions to be stable. So the first condition is Ki must be greater than 0. It must be positive because we need all of those that first column values to be positive. The second one is that this also basically must be positive as well. So we need to solve for essentially some of these bounds. And we can look at it in terms of essentially the bounds right here. So the bounds are Ki must be positive, and Ki has to be, we can kind of see that, Ki must be less than, put that in here, it has to be less than 4 times 200 plus Kp. 4 times 200 plus Kp. So these are our bounds to be stable. So we're now dependent, again, we can't just tune this without kind of knowing where we're at in the system, and we must be stable. So it was really, really, really critical. Very, 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 very important. So we actually, kind of did this already, and we went through, and we can actually look at some values. And actually, we can kind of see. Let's set, for example, let's set Kp to 100. Actually, we can actually see this right here. So we can actually see this system in action. So let's say we set Kp to 0.1, and let's look at our bounds. Actually, let's let Kp be like in this system 100. Let's say this is 50. If we look at our pole locations, oof, that's not nice. Let's look at it numerically. So if we look at our pole locations, we have one real pole, negative, left-hand plane, and we can see here that we're stable, right? And does that satisfy our condition? Well, we said that we need our Ki to be greater than 0. That's true. And we need Ki to be less than 4 times this. So Kp is 100. So Ki, which is 50, is less than. So is 50 less than this? True, indeed, indubitably. I'm really bad today with my awful jokes. It's not fun. It's not funny. Don't make jokes. If it's 1300, it's false. So let's go ahead and let's look at kind of the system response here. So we're going to say, and I'm going to just increase this to 2000. Same thing here. And let's start with that first system. Let's look at the poles. So when we had Kp was 100 and Ki was 50, let's look at our poles. And we see that we have a 0 here. That's shifted a little bit. We have a pole here, pole here. This system should be stable. Let's verify that with our inverse Laplace transform. We're going to vary this system. Again, I'm going to increase this to 2000, but we're just going to look at it and see. We're going to see the same response. Let's shift enter. Oh, let's open it up. Kp, I believe, was 100. And then Ki was what? 50? What did I do? Ki was 50. Let's put it here. Okay. And we see, okay, this is a response. I mean, it's not, the performance kind of is a little bit interesting. As we increase Ki, we see we're improving, right? That steady state performance, we're increasing. Let's see what we said with Ki. Let's see. Lightly damped and unstable. As you increase critical value, it becomes unstable. But the benefits of Ki, it limits and increase the order of the system. And the poles are shifting left. We're stabilizing, right? So we're stabilizing that system, and you see the response is improving. But we know, let's go increase further. Actually, let's do 1,000. We know that once we hit 1,300, or actually at 1,300, we know at least it would be bad. As you're approaching 1,200, it's not really great either. And actually, you can see already here, I think that's the old. My Mathematica is fighting for its life right now, so. I appreciate your response. So see, we're starting to kind of get a little bit, it's not looking good. And then by the time we hit 1,300, we can see here, we've pushed it beyond our limit. We're no longer stable. And now we can be in trouble. Once it starts to, yeah. So you can see we're basically almost resonant now at this point. So that's the danger of that integral control system, the PI control system in particular. So you can kind of see the response here, like this is looking nice, but once you kind of shift here, you can see the response here, very similar, no longer stable, and we're in trouble. So that is PI control. So you get stability, you get better, faster convergence, as you can see, but you can risk instability. So be careful out there in your control systems. Next time, we're going to do full PID. And that's going to be kind of fun to see it all put together. The math gets really nasty. We're varying 3 things at once. We've lost all physical control of the system and our intuition because everything's changing, and it'll be very fun. So we'll see you next time. Thanks. Bye.